Welcome back to day 8 of the 2024 Advent of Code. Let's take a quick look through this problem. We have another grid problem. We have a bunch of antennae which are indicated by anything that's not a dot. It has a frequency indicated by this, and we have a 2D grid where each antenna occupies an integer position. We are trying to identify the antinodes which have nefarious effects applied by the antennas, and these are based on the resonant frequencies. Specifically, we're told here that an antinode happens at any point that's in line with two antennas, where one is twice as far away as the other, meaning that basically we get two antinodes, one on each side. Technically, this description is not really precise, as there's also the theoretical possibility of having two antennae like this, with one of them 2/3 of the way in between them. This would also satisfy the requirement of being in a line and having one of them twice as far away as the other. But here we are explicitly told that it's just the two that are outside. So if we look here with three antennae, we have these two antinodes created by the first two, this antinode created by these two, the other one would be off the map, and this antinode created by these two, where the last one would also be off the map. If antennas' frequencies don't match, they don't create any antinodes, so they don't interact with each other, and capitalization matters, so the capital A here does not influence our result, but there is an antinode caused by these two lowercase a antenna that is on top of this one. Antinodes that are on top of other antennas are still counted. So looking at this example here, we have a bunch of antinodes, these two caused by the A's, this one caused by these two A's, which also has one here, and then a bunch caused by the zeros. And if a position has two antinodes caused by different pairs of antenna, we do not want to double count them. We want to know how many total unique locations have antinodes that are within the bounds of the map. As this is a grid problem, we can once again grab our grid by taking each line, and the strip here is important to remove the white space, because otherwise each line would have a trailing new line, which would mess with our data. I guess converting it to a list here isn't really necessary. And then what we want to do is we want to map each position to the antenna. So firstly, we need to know the bounds of the map, so let's grab that as rows and calls. And then we want to find the position of each antenna. And because we do not care about different frequencies of antenna, they never interact, we can store our antennas as a map from the frequency label to the list of coordinates that have antenna of that frequency there. So for each row, and for each column, if the character is not equal to a dot, because the dot represents the background, then we can add that to the antenna. So if the frequency character is not currently in the antennas map, then we can initialize it to an empty list, and once we have that list, we can append the current row and column coordinate. So if we print out the antennas for the test, we can see that the antennas with frequency 0 have these coordinates, and the antennas with frequency capital A have these coordinates. Now we just need to locate each of the antinodes. In order to do that, we need to find each pair of antenna and then locate what the antinode positions would be. So we'll have one of them which we'll label R1, C1 for its coordinates, and the other one R2, C2 for its coordinates. The difference between these two is R2 minus R1 and C2 minus C1. And what we're basically doing when we want this antinode to be twice as far away from this one as this one is we want to take this gap and extend it over to here. And likewise, we want to take this gap and copy it over to here. And so this position here would be this minus this, which is R1 minus R2 minus R1, which becomes 2R1 minus R2. And so the coordinates of this are 2R1 minus R2 and 2C1 minus C2. We get the same thing on the other side, really, because without loss of generality, we could interchange these two coordinates without changing anything. But just for completeness, this one is obtained by taking this and adding this. So we'd get R2 plus R2 minus R1, which is just equal to 2R2 minus R1. And so the coordinates of this one will be 2R2 minus R1 and 2C2 minus C1. Therefore, we just need to go through every pair of matching antenna. And so we can start by going through each set. The exact frequency doesn't matter. We only needed it to track which group was which. And so we can iterate through antennas.values, which only goes through the values of a dictionary. So for each array of antenna coordinates, we can loop through each pair. In order to do this, we can do for I in range length array, for j in range I plus 1 to length array. Basically what this is doing is I goes up from, if we have an array of like length 3, for example, I goes up from 0, 1, 2, and j goes up from I plus 1 to the limit. So we would get 1, 2, 2, and then this would have no valid values. And so all of the iterations of the loop would go through each pair of elements, or sorry, this would be 0, 1, and then 0, 2, and then 1, 2. So it'd go through each pair without duplicating because we don't want to check the same pair of antenna twice. Now, technically, another way you could do this is by including the antenna in the other direction and then only doing one of these sides, because the other side would be covered by when you swap the antenna around. Or because you need to deduplicate anyway, you could just check both sides with the duplicates included, but that's not efficient. So we want to keep the positions of the antinodes as a set so we can get deduplication. And now we can just implement the arithmetic from earlier. So R1 C1 is equal to the ith element, and R2 C2 is equal to the jth element. And then we just do 2R1 minus R2, 2C1 minus C2, and the other antinode is 2R2 minus R1 and 2C2 minus C1. And at the end, we just need to filter for the antinodes that are in the bounds of the grid. So what we can do is we can say antinodes print the size of the antinodes if we filter each of the antinodes where the row is between 0 and the number of rows, and the column is between 0 and the number of columns. And that will give us the solution for part 1. What I was saying earlier about including duplicates but basically checking the only one side is essentially, instead we could do this, add a condition to make sure we don't check the same antenna against itself because that will produce false antinodes, and then just drop one of these lines and that would still give us the same answer. It's entirely up to you which one you think makes more sense. I find this one nicer to look at. And with that out of the way, I will interrupt this video for a second before we move on to part 2 to discuss a thing that a lot of you are surely already aware of, specifically because I've been calling attention to it for the past couple of days, which is the LLM issue with people cheating on the leaderboard. So going through all of the days, you can see some pretty obvious evidence of this. Even today, for example, there is no way that anyone could possibly solve this problem in part 1 in 14 seconds. Yesterday, you have several people with obviously cheated scores, including one person whose GitHub specifically shows that they are automating using Claude, which is an LLM. Now, to be absolutely clear, I do not condone harassing anyone, and I absolutely do not encourage anyone to go harass these people because that would not accomplish anything, and that does not make you a good person. So please do not harass people, as that is not what I want. Rather, what I want to do is call attention to this issue and that the organizers of the Advent of Code are aware of this, and that the lack of action is not because of lack of willingness, but rather because there's really no good solution to it. And this is something that I discussed with him earlier today. And so I wanted to give a bit more insight and transparency into our conversation. So firstly, I wanted to call awareness to this issue just so any casual competitors who aren't really paying too much attention and haven't noticed the cheating don't think that it's just because they suck. The fact that you're not getting sub 30-second scores on problems like these is not because you're not good enough, but it's because you're actually doing it legitimately and not cheating. So that's one reason that I want to call it the AI problem. And the second reason is because this is a thing that a lot of people are aware of. And to a lot of outside observers, it seems like the organizers just don't care or aren't aware. This is something that is specifically mentioned on the website, which is that using AI to get on the leaderboard by automating solutions is specifically discouraged, and the organizer specifically told people not to do this. And up until this year, asking nicely has mostly worked. People have more or less cooperated and just played it nice and played fair, with only a couple of people cheating. Like last year, there were a small handful of LLM cheaters, but they didn't occupy too much of the leaderboard, and they kind of disappeared after a couple of days because the LLMs weren't able to keep up with the problem complexity. Unfortunately, this year, a lot of people have started straight up actively disrespecting his work. So I talked to him via email, and he's given me permission to share his responses because he also agrees that this is a big issue, and we both think that sort of discussing the context behind this might help rebuild trust with the Advent of Code and trust in its legitimacy and seriousness. So from his email itself, we see that the big change this year basically is that asking the community nicely is no longer working. This is the 10th year of the Advent of Code, and for the past 9 years, everything has been fine. However, this year, there have been issues with basically all of the things that are discouraged, overwhelming the website, which means DDoSing it. As you might remember, day 2 had some issues where the website just stopped working. That was not because of the organizer's fault. That was because people were actively attacking the servers. People sharing answers or uploading their inputs to GitHub, which is also strongly discouraged. Streaming while the leaderboard is still up, and using LLMs on the global leaderboard. These all weren't problems in the past because he just asked nicely and people behaved. But for some reason, this year, people have just stopped respecting him. And additionally, something else that has come up is that it's not just that more people are cheating, is that people have specifically been emailing him, telling him that they've seen his requests not to use LLMs and they don't respect his work and will be using LLMs regardless of what he says. This is clearly a problem of dishonesty and complete disrespect and disregard for his hard work. And so there is no solution that will possibly work because any solution we can come up with more or less requires some amount of honesty and human decency. I discussed a couple of solutions with him, and if you do have any ideas that you think could potentially help mitigate or solve this problem, please do let me know, and I will relay them to him and maintain contact with him. I was surprised to learn that he is actually already familiar with my work. When I emailed him, I wasn't really sure what to expect, but he actually already recognizes me. And we went over a couple of ideas, and we agree that it's unlikely that any of these would really help. So the purpose of my message is to hopefully restore some sense of trust and openness. I really appreciate that he was very open with his responses and willing to have a serious discussion with me on this issue and give me permission to share this with you. And while I know that me talking about this is going to do absolutely nothing to solve the problem itself, I hope that presenting this openness to you can show that this is a serious contest that the organizer is taking seriously, and this is a problem that the organizer is aware of, but not for lack of trying. Nothing can really be done. Anyway, I want to get back to the rest of this video, so I will post a link to this Google document, which is unedited from our email thread. I'll post this in the comments, and I will post this on my Discord. If you would like to read a bit more into this, I welcome you to read this in your own time, but let's get on with part 2 for this video. For part 2, it turns out that the antinode positions are changing. Instead of being at the two ends as previously specified, it instead occurs at any position that is exactly in line with two antennas of the same frequency. So basically, instead of just having those two positions, if you have two antennas here, all of these positions would be antinodes. And again, interestingly enough, there's no actual mention of there being antinodes between antenna. It seems that that just is not a case that needs to be considered. For example, stuff like this also would not need to be considered. So we need to update our logic for determining the positions of the antinodes, and this turns out to not be too complex. Once again, we have our antenna positions at R1C1 and R2C2, with the difference represented as R2 minus R1, that's the change in row, and the change in column represented as C2 minus C1. What we can essentially do is just repeatedly move in that direction all the way until we exit the map. And so we can start from R1C1 and each time just subtract delta R and delta C until we hit the edge of the map and stop. Likewise, we can go to the other side and we can do we can add delta R and delta C instead, all the way until we hit the edge of the map again on this side. For this case, I find it easier to check the antennas both directions, basically include the duplicates, and instead of going in both directions, just go in one, because the other will check when we check the antenna in the opposite order. The reason this is easier is because otherwise you'd basically have to repeat this loop statement twice, and although there are ways to avoid having to copy paste the code, ultimately it'll just end up a bit less clean. The way I did it during the contest involved just having two loops because I was already deduplicating the antennas, but since we have time here and aren't on a time constraint, we can work on making the code a bit cleaner. So again, basically the change in row is equal to R2 minus R1. We could also do R1 minus R2, it doesn't actually matter. And likewise, the change in column is C2 minus C1. Now, instead of adding these two antinodes, we can just do a loop. So we'll start the row and column at R1 and C1. Also, note that it's explicitly specified that the antenna themselves also count as antinodes, except if there's only one of that type. In other words, we do want to add R1 and C1 itself. So basically, while R and C are in range, we will add RC to the antinodes list, and then we will do R plus equals DR and C plus equals DC. Again, it doesn't matter if you make these plus or minus, and it doesn't matter if you do R2 minus R1 or R1 minus R2, as long as the signs are the same, obviously. If you had them flipped, then it would go in the wrong direction, but flipping the signs would make it go in the opposite direction, and it doesn't matter if you go this way or this way first, because the other one will be covered when you flip I and J around anyway. And so this will give us the solution for part 2, or if you want to be a bit more efficient, you can get rid of the filter here and just do the length of the antinodes list. It doesn't really matter for performance because the set is so small, but just a little optimization you could do. In any case, thank you very much for watching. I hope you learned something and I hope you enjoyed this video, and I'll see you again next time.